In this lecture, we're going to start going into the actual data that we can acquire from a 1H or proton NMR experiment. And this should, for the most part, actually correlate well to all the nuclei. In fact, the 1H NMR spectrum is probably the most complicated, but the complications make it the most useful. And once we learn it, it just makes learning all the other nuclei all the easier. So the focal point will really be 1H or proton NMR for the remainder of the section, with a few discussion points about carbon-13 NMR, for example, in later lectures. Okay, so we're going to get into it with understanding the NMR spectrum. The first thing we should do is identify what the NMR spectrum is. Okay, so what we get from doing the NMR experiment is an NMR spectrum. So the data obtained, and a better word is probably acquired, is the NMR spectrum. Okay, so what does an NMR spectrum look like? Well, it looks like a graph where the x-axis is labeled with an interesting unit, ppm, and the y-axis is intensity, and intensity is actually unitless. ppm is actually the units for the x-axis, and we always label it as ppm, but indeed this is sort of correlating to the frequency. So this correlates with the frequency. And what we would see is kind of like what we had been looking at in our examples. That is, you have some peaks. They're going to look a little bit different than this, but we see these peaks. And these peaks just have what are called ppm values, which is actually the unit for the peak, as opposed to some formal, a more formal value for the frequency. Okay, so let's break into the units of the x-axis a little bit. So ppm, again, the mainstay of the x-axis label for NMR spectra. ppm correlates, or is, parts per million. Okay, and for those of you that have taken our Equilibrium and Quant, our sophomore analytical course, this shouldn't be an unfamiliar series of words, but in this context, it may not, and it likely doesn't make sense. So again, our x-axis label is actually a unit. Now, why? Well, just to be frank, because it makes the numbers look better. So a lot of visualizing data is choosing appropriate units for things so that the data can be readily disseminated by our human minds. Okay, so let's look at this for just a couple of nuclei. A typical 1H NMR spectrum will then look like this. We have, I'm not going to label the y-axis, that is intensity, and it's unitless, as I mentioned. The x-axis is labeled parts per million, and it typically spans from 14 to 0. Now, you'll notice another oddity about this, and that is that the numbers actually become smaller as we move from left to right. So left, we're going to start with the bigger numbers, and we're going to go down to 0. So first of all, observe that we go from increasing frequency from right to left instead of left to right. Now, the other thing to make note of is I didn't get too far into it, but I can actually have negative numbers. Okay, so 0 is on the right. Higher numbers are on the left. The highest we typically go is 14. We actually often just cut that off because there's nothing that goes too far out to 14. So we would probably cut it off around 10 for most cases. If we have aldehydes, then we'd extend it to 12. It's just a zooming trick within the software that processes the NMR data. In a carbon-13 NMR spectrum, that range would extend to larger numbers, as the carbon-13 chemical shifts can have a much wider range of ppm values. So you would have maybe 300 at the high frequency, or high ppm end, and then the lowest you would see is like -50, where zeros somewhere closer to the right. So once again, we're going increasing frequency, because increasing frequency correlates directly with parts per million. So we're going to label this parts per million, but I want you to think of it as frequency. And we're going to go from left to right, going smaller in terms of the ppm value and thereby the frequency value. Okay, so I cannot emphasize this enough, how these correlate with each other. A higher ppm value, what's kind of a weird word, how about larger? A larger ppm value corresponds with a larger frequency of absorption. Now, we'll be working almost exclusively with ppm in this course, but Hertz will only come in at the very end of things in a very special circumstance. But let's spend some time going and figuring out why we would ever want to use this obscure unit as a label for our x-axis. Okay, so that is to say, let's go from our frequency values, which are in Hertz or Hz, often megahertz, right? But going from Hertz to ppm. Okay. So let's look at water, for example. So water, which is H2O, has an NMR spectrum with one peak at 300.0000456 megahertz. Okay. Water has this as its megahertz value for its resonant absorption to flip from the alpha state to the beta state in the 1H NMR. Now, I'll just mention this briefly. Water has only one peak, because if we label this as A, this is also A. Both of the hydrogens are in identical chemical environments within water. Okay, so what we want to do is, first of all, take this value and reference this to the standard. So, number one, reference the value to some standard. Now that's where an interesting molecule comes in, and it's called TMS. So there are a few examples of different types of referencing agents, but the most common one, and the one that we will use experimentally in the lab, is TMS. So TMS is tetra, that's where the T comes from, methyl, that's the M, and silane, that's the S, TMS. Okay, so tetra is 4, methyl is CH3, and silane refers to a silicon with no oxygens present directly attached to the silicon atom. Okay, so we have 4 methyls on silicon. Okay, now a lot of times we buy our NMR solvents with some TMS already spiked into it, so we don't have to handle TMS directly. TMS is a great reference standard for a few reasons. Number one, for the question why TMS, is it's inert. That means it's unreactive for the most part. We can find some ways to get it to react, but for the most part, it's not going to do anything. That's a really important point, right? Because if we're doing an analytical technique, we want to just analyze the chemicals that are present. We don't want to observe a chemical reaction unless we're trying to do a chemical reaction. But during the course of the analysis, we don't want to inadvertently do a chemical reaction, so it's important that it's inert. Second thing is we want to be able to get rid of it easily, and we can because it's low boiling. So there's a lot of things that we could use as a reference standard that are inert, but this being low boiling, it's easily removed. Okay, so third thing is it readily mixes / dissolves with organic molecules. Okay, and then for the purposes of NMR, a last benefit is that all 1H atoms are in the same chemical environment. And that's also true of the carbon atoms. Okay, so remember carbon atoms, we can only study carbon-13, so we just rely on the naturally abundant carbon atoms. Okay, it's not like we're just riddled with carbon atoms, whereas for the most part, all hydrogen atoms present are the NMR active, are an NMR active isotope hydrogen 1. Okay, but what's cool about TMS is that every single one of the carbons are in the same chemical environment. Every single one of the hydrogens are in the same chemical environment. So if you actually, now the bond line structure of TMS is simple, right? We only have to write the SI, but if we went ahead and wrote all of the hydrogens explicitly, you would be a bit overwhelmed, right? There's 12 hydrogens on this molecule. Similarly, there are 4 carbons. I mean, 4 is a smaller number than 12, but it's still, for a reference standard, we would like to just see one peak. So it's true, though, that there's only one peak in the 1H NMR spectrum and the C13 NMR spectrum. Okay, now that's due to symmetry. And it turns out that all of the hydrogens are in the same chemical environment, right? They're all, if you look at hydrogen on one carbon, it's attached to has a bond to a carbon that has 3 hydrogens and is directly attached to silicon. If we go anywhere else in the molecule, we're at a hydrogen that's bonded to a carbon that has 3 other hydrogens that's directly attached to silicon. Okay, so due to symmetry, silicon makes a tetrahedral center, by the way, but due to symmetry, we're going to see that all of the hydrogens are in the same chemical environment. All the carbons are in the same chemical environment. And as a result, the molecule will then give only one signal because there's nothing to differentiate. All of the hydrogens are the same. All of the carbons are the same. Okay, so we see one peak. That's great. That means it doesn't convolute or kind of complicate the NMR spectrum with a bunch of peaks that we have to recognize are part of the reference molecule. You know, it's like, oh, I just want to see one. Well, TMS is great for that. Now, additionally, kind of an added advantage is that TMS, and this isn't critical, but it's really helpful, TMS pulls the one peak away from most other peaks. Now, what we've done is we've decided to define this as TMS is defined as being 0.00 parts per million in the NMR. Okay, so this is our reference peak, 0.00 parts per million. Or, if you want to go into megahertz, or 300.000 forever megahertz with a 7 Tesla magnet. So recall I said that when we put our hydrogens in and we look at a low resolution spectrum, we're going to see one peak corresponding to the 1H atoms at about 300 megahertz. If we zoom in though, and pull that apart and resolve that peak into the various types of hydrogen that are present based on differences in their chemical environment, some are going to be at 299.00 blah, blah, blah. And like I said, with water's at 300.000456. So they all kind of are moving around. None is exactly 300. Well, what we've decided is that TMS is actually quite a bit different than all the other hydrogens. So we're going to set that one equal to 0, or excuse me, to 300.00. It's just a choice. TMS is 300.00, and then we're going to reference everything else to it. Now, whenever I say what's cool about that is if I go up to an 11.8 Tesla magnet, which I said was called a 500 megahertz NMR, because protons absorb at about 500 megahertz and flip from the alpha state to the beta state, TMS now is 500.0 on forever, and so on and so forth. So the name of every NMR actually comes from the, whether it's 300, 500, 700, 900, 1.1 gigahertz NMR, that corresponds to the resonance absorption frequency for tetramethylsilane, TMS, in every case. So TMS determines the name of the instrument. Like, we don't call it the 7 Tesla NMR, we call it the 300 megahertz NMR. Okay. So a lot of advantages, okay? Now, what we want to do then is go back to our idea of going from megahertz to parts per million. I've already given you a little bit of a hint, not a very good one, but I've said already that TMS is 0.00 parts per million, or in the case of a 7 Tesla magnet, 300.0 on forever parts per megahertz. Yeah, 0.00 parts per million, 300 megahertz. Okay, now let's actually do the math to get from parts per million, excuse me, from hertz into parts per million. Okay, so back to converting megahertz to parts per million. Okay, so what we want to do is first reference to a standard. In our example, our example was H2O, which has 300.000456 megahertz, and our standard is TMS, which is 300. Okay, so what we're going to do is we're going to subtract these from each other. Now, how many decimal points? What's the significance of TMS? Remember, we define TMS to be the 0 point or the absolute 300 point. So we can add as much significance and precision onto this measurement. We want to match the measurement that we're trying to reference. So what we're doing when we reference something is we're subtracting its value from the observed value that we're trying to understand. So the new value that we get is 0.000456, and we have megahertz to megahertz. Okay. Now, what we want to do is divide this by, and I'll specify this, divide the referenced value by the TMS absorption, and then multiply by 1 million. Okay, so this is kind of like, if you think about percentage, you take a number divided by a number, and if you want to convert that to a percentage, you multiply it by 100. Turns out here, we want to multiply things by 1,000,000 to make them look nice. Okay, so what we have here is 0.000456 divided by 300 times 1,000,000, which is 1 times 10 to the 6th. If you do that math, first of all, what you do is you cross out the megahertz units. So now we have something that's sort of unitless, except for the fact that we're converting this, we're multiplying it by 1,000,000 to tell us that this is some parts per 1,000,000 of something. And the answer that we get if we do the arithmetic is 1.52. So that if we did a percentage, we'd write this little symbol here to remind us that it's a percentage. But here, what we're going to do is write the ppm value to tell us that we multiplied this by 1,000,000. Okay, so the point of this is to say that once we reference this, we're going to get to a number that is much more useful to us, much more user-friendly, if I had to say this. Okay, the number 1.52 is much easier to remember than the number 0.000456. And maybe it's not harder to remember. Maybe it's, maybe it's easy to remember 0.000456. Okay, but it's a lot easier to say 1.52 than adding a bunch of zeros in front of it. So this tells us this would be the x-axis value for water. The x-axis value for water is 1.52 parts per million in the 1H NMR spectrum. Okay, so we use TMS to first subtract the 300 from it, and then we divide it by the frequency of TMS to give us our per million quantity. So the parts that we then take per million. Now, what's super cool about this is the value will not change if, and by value, the ppm value will not change if you change to a larger magnet. That is wonderful. Okay, so imagine I'm doing science at Ripon and I'm making molecules and I'm observing their NMR properties by using my 7 Tesla magnet, which has a resonant absorption of TMS at 300 megahertz. Okay, and I want to report that data. Now, for a lot of instrument types, a lot of other analytical techniques, I would have to specify for every measurement that I'm using a 300 megahertz instrument. Now, I would always say that just, for the sake of let's get that out there. But when I report this x-axis value, okay, it turns out that it will not change whether I've got a 300 megahertz NMR or a 500 megahertz NMR. The parts per million value will not change. Now that's really important to take away. That's another big reason why we use parts per million instead of hertz. The hertz value will change. When I go from 300 to 500, the energy gap increases. That allows us to see more subtle differences between the various hydrogen nuclei. However, due to the math, because we first take the larger value now, it might be 500 point blah, 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 blah. We first take it, subtract 500 from it, and then divide it by 500, the ppm value actually stays the same. The hertz value changes, the ppm value will not change. So that's another reason why we report our relative frequencies as parts per million values. TMS is always then 0. Okay, let's do that math really quick. So why is TMS 0? Very easy to do. If we observe that it's 500.000 or 300.0000 is forever, what's the first thing that we do? So we've observed 500 on a 500 megahertz instrument. We subtract the TMS absorption. We divide by the TMS absorption 500 minus 500 divided by 500 is equal to 0. Now the label is parts per million. And yeah, I could multiply it times 10 to the 6th. Sure. Now if I take 300 minus 300 divided by 300 and I multiply that by 10 to the 6th, I still get 0 parts per million. So TMS is always 0. Because TMS is always 0, and we've defined it as our reference standard, water, even though it would have a much larger megahertz value on a larger magnet like a 500 megahertz NMR, because you subtract 500, divide by 500, multiply by a million, you get the same parts per million value. So looking at this, we are then ready to, sort of with this knowledge, and I guess, for lack of a better word, the anatomy of the NMR spectrum, we're ready to learn into the attributes, move into the attributes of the data that we will expect to acquire from an NMR spectrum.